lifetime or the age lifetime. Okay, so limiting distribution of the spent or age lifetime, basically delta t, is it not? We denote this by delta t. So by definition, what is my delta t? This is t minus s of in t. This is the spent or the age of the renewal process. Okay. So now what happened? Because at t you have a renewal, which is the number of renewal is nt. So the age and s of nt is the epoch. So t minus nt is the age or the spent lifetime. So now I am saying that delta t is greater than x. So what is that mean? That means basically s of nt, which is less than t minus x. Is it no? This is same as my s of nt is less than t minus x. So that means basically what it means. That means in the interval t minus x to t, because at time t we have the renewals, number of renewals is s of nt, and hence since s of nt is t less than t minus x, that means there is no renewals between t minus x to t. Okay, so no renewals in t to t minus x to t. So because already we know what is the probability distribution of your residual lifetime. So for there actually, as you told, that nu t is greater than x if and only if there is no renewal between t to t plus x. So now if you try to write down these things, that means this is same as nu of t minus x is greater than x. Is it not? Because there is no renewal between t minus x to, so now this is my, if you think of as a new t, say maybe t1. So now there is no renewal between t1 to t1 plus x, and that means basically this is t minus x to t. So what I am saying, that delta t is greater than x if an implies nu of t minus x is greater than x. Okay, so what I can write down there, this implies probability of delta t greater than x is same as probability over nu t minus x is greater than x. So this implies I can think of, so if you look at the complement of this set, then probability of delta t is less than equal to x, which is the distribution functions of the spent life delta t. Then what I can write down, this is same as my probability of nu t minus x is less than equal to x. So already we know how the probability distribution for this spent lifetime, sorry, the residual lifetime nu t minus x looks like. So from there, if you see, this is something like that f of t, because there you have f of t plus x. So now if you replace t by t minus x, then this is f of t minus 0 to t minus x 1 minus f of t minus y, and then d of my. So if my x is less than equal to t, and then you check this is 1 for x is greater than t. Okay. Okay. So now suppose my f is non-lattice, because we have already shown that for non-lattice case I know these things, so that limit equals to probability nucleus equal to x, which is same as. So now for non-lattice case, that limit t equals to infinity, probability of delta t is less than equal to x. This is same as my limit t goes to infinity, probability of nu of t minus x is less than equal to x. So now, so as my t goes to infinity, the t minus x for fixed x is goes to infinity, and then you have the same thing. So that means 1 by mu 0 to x 1 minus f of y of dy. Okay. So what we have seen here, that the limiting distribution for spent lifetime delta t. So there we are using basically the equivalency of delta t greater than x if and only nu of t minus x is greater than x. Okay. Okay. So let us consider, because I talk about the three things, and another is the total life. So I can write down as a theorem form. So let beta t be the total life of a renewal process, and t, then what will be the distributions of beta t, then probability of beta t is less than or equal to x, which is f times maximum of t and x minus 0 to t probability of beta of t minus y less than or equal to x, and then d of fy. Moreover, if f is non-lattice, what we have, that the limiting distribution, that limit t goes to infinity, probability over beta t is strictly greater than x. Okay, you can put beta t less than or equal to x in form, but I just try to put beta t still greater than x. This is 1 by mu x to infinity zeta of df of zeta. Okay, this is zeta of d of f zeta. Let us try to prove these things. So here also we try to consider the conditions on my t1, which is the first renewal or the first interval time t1. So let bit kt I am considering, which is probability of say beta t is greater than x, because if you look at this one, beta t less equal to x, I have in terms of, again, this means if you look at that set which is 1 minus kt, then from here actually you have 1 minus k of t minus y and so on from. Okay, so that means I try to write down, because this is in an integral equation form and it is not in a explicit form, it is an implicit form way. So I try to define first that kt, which is the probability of beta t is greater than x. So now if you look at conditioning on t1, then what I have, that probability of beta t is greater than x given t1 is equal to y. Okay, so beta t, which is your total lifetime, so beta t, which is my delta t plus gamma t. So this is nothing but my t minus s of nt, and this is nothing but s of nt plus 1 minus t. So now this is nothing but s of nt plus 1 minus s of nt, which is nothing but my t of nt plus 1, is it not? Because s of nt, which is the n partial sums and so on of ti, so I have my this quantity. This is same as my probability of t of nt plus 1 strictly greater than x given t1 is equal to y, is it not? So now these things actually I can write down. This is 1 if my y is maximum over t and x, is it not? So given t1 is equal to y, if y is greater than my maximum over t and x, then the probability of these things is 1. And what happens if my y is less than equal to t? So in that case, I have my k of t minus y, which is nothing but this one. That beta of t minus, it means you can think of that it start at my point y and then you need to go up to t minus y. So because t1 is equal to y, that is the first renewal happening, and 0 you have otherwise. Okay, so if y, which is greater than maximum of t and x, then this the probability of these things is equal to 1. Okay, so then what I try to write down, I try to write down my kt in terms of the total probability, like in my previous case. So my kt, I can think of, this is 0 to infinity probability of beta t greater than x given t1 is equal to y and then d of fy. This is the by total probability rule. So then what I can have, so I can then put 0 to t k of t minus y dfy and then plus maximum over t and x to infinity, I have my d of fy. Is it not? So then if you try to write down, because d of fi we have, this is a distribution function, so at infinity it gives you 1. Then I have, this is 1 minus f of maximum over t and x, and then minus 0 to minus or I have this part, I have 1. So this is plus 0 to t k of t minus y d of fy. Is it not? So that means if you look at what I want here probability of beta t less than equal to x. This is that means 1 minus kt. So this implies 1 minus kt, which is equal to f of maximum of t and x, then minus I have 0 to t and then k of t minus y, k of t minus y d of fy. Okay, so have I done mistake somewhere else, or this one is 0 to t, I have k of t minus y and then this part, so you have your plus okay. So this is your beta of t. So this is implies probability over beta t is less than equal to x, because kt I consider beta t is strictly greater than x, so 1 minus kt, that should be beta t is less than equal to x. Is it not? So now if you try to write down, this should be equal to f of maximum over t and x and then minus, or you can write down from here, because I want this is beta of t minus x, so 1 minus k over t minus y, then I have to plus, write down 0 to t dfy, and then f of 0 is equal to 0 maybe, then what I have, I need to minus 0 to t d of fy. Is it not? So this is f of t minus f of t. I have then f of maximum over t and x minus f of t plus 0 to t. I can write down that probability over beta of t minus, oh, I have to put t minus y, t minus x, t minus y is less than equal to x of t of fy. Okay, this part I have. What I have here, I put maximum over t and x, 0 to t beta t minus fx. This is minus sign is comes into picture. I don't know whether I have done mistakes or not, but this one is positive. Okay, so maybe this one actually I can change it here in my theorem. I need to check it, okay? I'll check it in the next class. This one, okay, at least the first part, I'll check it. Okay, but this one is correct, that kt, which I have in this form. So now to prove the second part, let's see. Now the 1 minus f of maximum over t and x, this is a non-negative, bounded and integrable functions. Is it not? Hence, what I can write down, that limit t goes to infinity of my kt, this is 1 by mu 0 to infinity, because this is in the, again the renewal theorem form, no? Then we can use this lemma, previous lemma, and also this key renewal theorem, the Smith's key renewal theorem for non-lattice case. What I can write down, that this is 1 by mu 0 to infinity 1 minus that h of y dy, no, I wrote down that f of maximum of tx, okay, and then dt. Is it not? So now I try to write down in the given form. So this part actually I can write down, this is 1 by mu 0 to x 1 minus f of x ds. If t lies between 0 to x, then I have maximum of t and x is x, so I have this part, and then plus x to infinity, this is 1 minus f of s and then d of s. Is it not? This part actually I can write down. So this one I can write down, this is 1 by mu 0 to infinity 1 minus 0 to x fx ds, and then plus what I can write down, this one you check yourself, because already what I know that mu, which is equal to minus infinity to infinity 1 minus f of s d of s. Is it no? So from there I can write down, this is mu minus 0 to x 1 minus f of s d of s. Okay, because this is x to infinity, so in this case minus infinity is basically 0 to, because this is positive things I have. So then if you just add and subtract what I have, this is 1 by mu 1 by mu 1 plus 1 by mu, okay, I have 0 to x, so this is 1 minus 1, it got cancelled out, you have f of s minus f of x and then d of s. So now mu actually is nothing but your expectation. So that actually I can write down. This is 0 to infinity zeta df of zeta form. Okay, you check yourself. This can be done. So now these things actually again I can split my integral. This is 0 to x zeta df zeta and plus this is x to infinity zeta df zeta. So now this one you can write down that x fx. So if you use the integration by parts formula here, then what I have, this is x fx minus 0 to x f of s ds and then plus x to infinity zeta df of zeta. Okay, so now if you try to write down, this is minus, if you simplify these things, I can write down 0 to x f of s minus f of x and then d of s, because f of x it is independent of s, so I can write down in this form, and plus x to zeta, x to infinity zeta df of zeta. So now if you look at mu is equal to in this form, and what I have limit t goes to infinity at, just a minute. Hello? Yes, yeah, I have a class, I'm just in my room. Yeah. Oh, okay. Yeah, my room is open, so you can just okay, thank you. Okay, thanks. Yeah, sorry. So what I have, that mu I write down in this form. So there what you can write down here, that limit t goes to infinity of my kt, which is equal to 1 by mu x to infinity zeta df of zeta. Okay. Okay. Let us consider one example so that we can find out the limiting distributions of total lifetimes and so on, or maybe certain thing. So example says that, look at now the Poisson process case. So what it says that the mean total time of exponential distributed interval times associated exponential distributed inter-arrival times is larger than the mean life. Okay, so what is the mean life is basically mu. Okay, mean life is the mu of ti. So here mu is 1 by lambda, is it not? Because if I look at the ti, which is the sequence of exponential distributed interval times with parameter lambda, then the mean life, which is mu, in this case is 1 by lambda. Is it not? That is actually already we have seen it. So what I want to show, we want to show that expectation over beta t, this is greater than 1 by lambda. Is it not, for this case? Okay. So because this is the mean total life, mean total lifetime. Beta t is the total lifetime, and then we are considering the expectations. So that means the mean total lifetime. So what is this? because beta t you have, this is nu t plus delta of t, is it not? And again delta t can be written as in terms of nu t, and hence I can consider the expectation in a nice way. Okay, so what is my nu t is greater than x? This is same as, because what it says that there is nu t greater than x if and only there is no renewal between t to t plus x, is it not? So that means this is nothing but the probability of n of t plus x minus n of t, this is equal to 0, is it not? Because at t plus x, n of t plus x, that is the number of renewals at t prime is, and then nt, which is the number of renewals at point t. So then there is no renewals, means basically this minus this is equal to 0. That is the probability. And now what we know that the Poisson process, n is now the Poisson process, is it not? So n is now the Poisson process. Okay, in particular the renewal process is nothing but here the Poisson process. So we know that the homogeneity property, is it not, or the stationary property of your Poisson process. So now if you use this stationary process or the stationary property for this Poisson process, this is same as my probability of n of x is equal to 0, is it not? Because n of t plus h minus nt has the same distributions as n of h, is it not, for any t positive and h positive. So I have this n of x is equal to 0, and now this is nothing but n of x is equal to 0. That means it is nothing but e to the power minus lambda of x, is it not? We know that because n x it follows the Poisson distributions with parameter lambda t. So I have e to the power minus lambda x. So this implies probability over nu t is less equal to x is equal to 1 minus e to the power minus lambda x. Okay, that means again I have seen that the nu t is exponentially distributed, is it not? The spent lifetime, the residual lifetime for a Poisson process, that this is again the distributions of your nu t is 1 minus e to the power minus lambda of x. So this implies already we know that expectation of our nu t it should be 1 by lambda. Okay. So now what I have to show that expectation of beta t is greater than lambda. So expectation of beta t is nothing but expectation of gamma t plus expectation of beta t. So if expectation of beta t is basically positive, then we are done, is it not? Let's see. So now what is my delta t is greater than x? Again we know that this is same as my nu of t minus x is greater than x. Okay, so what I can write down that expectation over delta t, this is the age or the spent lifetime, mean of the spent lifetime. So this I can write down, this is my 0 to t probability over delta t is greater than x times d of x. This is not spent lifetime, this should be up to t. So 0 to t probability delta t greater than x, and these things I can write down 0 to t probability of, because delta t greater than x, I know that this is same as my nu of t minus x is greater than x of d of x, and already we have seen that probability of nu t greater than x is e to the power minus lambda x. It is independent of your t. So what I have, this is nothing but my 0 to t e to the power minus lambda x times d of x, and then you have 1 by lambda 1 minus e to the power minus lambda t. Okay, so this implies already you have seen that this is positive quantity. So expectation of beta t, which is expectation over nu t plus expectation of delta t, and then if you look at, this is 1 by lambda I have, and plus this is 1 by lambda minus either minus lambda t. Okay, so this is strictly greater than 1 by lambda. That means the mean total lifetime of a Poisson process is larger than the mean life, every mean life. Okay. So here actually we are using that distributions of limiting distributions of means the probability distributions of my residual lifetime and then the spend lifetime to calculate these things. Okay. So next we'll consider a new renewal process that is called the delayed renewal process. So delayed renewal process means basically you start counting little later, in the sense that so now you have your T1, T2, T3, T4 and T and so on. They are interval times, and what I know means for the renewal process we know that okay, the TIs they have IID distributions, but in this case they are the independent non-negative random variables, but the first interval time T1 it has different distributions compared to the other TIs. Okay, so if I write down, so let Ti say either equal to 1 be a sequence of independent non-negative random variables such that T1 has distribution G and Ti for I greater than equal to 2 have identical distributions. Say F. Now I do not S0 is equal to 0 and S of n which is again like same as summation over I is equal to 1 of x of T of I. Okay, and I define NDT which is the same as supremum over all those n such that my S of n is less than equal to T. Then the process NDT, okay, this D denotes the delay, is called a delayed renewal process. So here we want to know means so in this case the what is the difference between the renewal process and the delayed renewal process? Again, see it's a renewal process. Delayed in the sense that the first interval time D1 and the consequence other the renewal the interval times Ti they have different distributions. So the T1 has a distribution G and T2, T3, Tn they have the identical distributions F. Okay, that means something like that. Okay, so suppose something is going on, then you don't know from where actually it is coming, and then you start counted from here and so on. So that means that the interval time actually you are looking for their IID, but eventually actually it's happened from past. So that has a distribution say G. That means that T1 I have a distribution G, and then T2, T3 they have the identical distributions which I wrote down as F. So we also try to write down the renewal equation for delayed. I just put as NDT. Okay, what is that? So I try to write down again in the integral form. Okay, so again if you look at NDT given my T1 is equal to X, what is the expectation given T1 is equal to X of NDT? So this part is equal to again 0 if X is greater than T, is it not? And what I have 1 plus m of T minus X if my X is less than equal to T. because at point X I have the first renewal and then the other things, and if you look at the expectation of that part, so that means you can think of, okay, I have started from the point X and then the remaining time is t minus x, so that expectation, that is nothing but 1 plus m of t minus x, is it not? So because this is the impossible event, that's why that it is actually is equal to 0. So now if you denote my m, so what is your m? M is basically the renewal function associated with distribution f. Is it not? Okay. So now if I denote my MDT, which is the expectation of delayed renewal process NDT, then what I can have MDT, which is again I can use the law of total probability. This is 0 to infinity expectation over NDT given T1 is equal to x. Now I have dg of x, is it not? Because T1 has a distribution which is g. So I have dgx, and then if you try to write down, then you split this integral. What I have, this is 0 to t. Whenever x lies between 0 to t, then I have this is 1 plus m of t minus x. So I can write down this part of dgx, is it not? And then the other part actually it is 0. So this one I can write down. This is my gt plus 0 to t m of t minus x d of gy. Is it not? Sorry, g of x. So now properties of convolutions actually I have. What is the property of convolutions? You can check. So basically what I have, f convolution g is my g convolution of f. Okay, that is the property of convolutions. So in particular here actually I am saying that 0 to t m of t minus x dg of x. This is nothing but the convolution of m with g. This should be same as the convolution of capital G with small m. So that means I can do this 0 to t g of t minus x of d of mx. Okay. So thus, if you use that my previous the technical lemma, like what will be the solutions to your renewal equation, then I know that MDT is a solution of the renewal equation MDT, which is my GT plus 0 to t md of t minus x dfx. Is it not? So MDT, which is a solution of the renewal equation, this renewal equation, because in my technical lemma I wrote down that MDT, which is equal to HT plus 0 to t h of t minus x dfx. So from there, that z of t is equal to some ht plus z of t minus x. Then the solutions exactly is given by in this form, no, that which is equal to gt plus 0 to t g of t minus x d of mx. So that is why actually we are writing down here mdt exactly gt plus 0 to t g of t minus x dmx. Okay, from here actually we are having, so the mdt, which is a solution of the renewal equation, this form. Okay, So we try to show that if my f is non-lattice, then MD satisfies the renewal theorem. To prove that, what I have to show that means basically that I try to show that, okay, for any say H positive, I try to write down MDT minus MD of t minus H and then put t goes to infinity. Okay, so either this is H that H by mu or not, is it not? That is the if you look at the Becquerel's theorem, from there that is we have. Okay, so we try to show that similar thing is. So for any t is greater than H, what I can write down? MD of t minus H, this should be my G of t minus H, and plus 0 to t minus H, M of t minus H minus X, and then D of Gx. That is actually we have seen, is it not? That MDT satisfies these equations. So this implies, if I now write down MDT minus MD of t minus H, if you just recall my Blackwell's renewal theorem, they are actually, for non-lattice case, they try to write down that what happened as limit t goes to infinity, MDT minus MD of t minus H, and that should be H by mu and something like that, actually try to show that. Okay, so this part actually if you calculate, what I have, this is GT minus G of t minus H. Okay, this is GT minus G of t minus H, and then plus what I have, 0 to t M of t minus X dgx minus 0 to t minus H M of t minus H minus X, and then d of G of X. Is it not? So now if you just look at these differences, what I can write down, this part, only this part, this is nothing but my 0 to t M of t minus X minus M of t minus H minus X time d of G of X, and then this is remains same. So this is G of t minus G of t minus H. Okay, so I can write down this part. So these things actually I am denoting some mathematical A, and I try to write down what happened to this case. So now this A I can decompose as a two terms. So A1 plus A2, and what is my A1? Where I am writing down A1, this is say 0 to t by 2, and then I try to put t by 2 to t, M of t minus X minus M of t minus H minus X to dgx, and my A2, which is t by t to t M of t minus X minus M of t minus H minus X of d of gx. So now what I can write down, that by Blackwell's theorem, because m is the renewal function, what we know that limit t goes to infinity, okay, for the non-lattice case, M of t minus X minus M of t minus X minus H, is it not? This is same as my H by mu. Okay, and what is my mu is now in this case expectation of t2 should be, because m is corresponding to the interval times t i's for I greater equal to 2. So mu should be now expectation of t2, because t2, t3, t and so on, they have the identical distributions f. Okay, and hence since this limit exists, what I have, that this function, and hence this function m of t minus x minus m of t minus h minus x is a bounded function of x. Is it not? So therefore, what I can have that my a2 this is goes to 0 whenever t goes to infinity. Okay, because m of t minus x for large t, okay, m of t minus x minus m of t minus h minus x, this is bounded, okay, and then g, this is the integrable the distribution function, so d a g b you have, and hence as t goes to infinity, now if you look at that measure, so because it is t by 2 to t, so that is why this a2 term that goes to 0. And what about my a term is going to a1 is going to h by mu as t goes to infinity. So thus if you combine these things, so this implies limit t goes to infinity m dt minus md of t minus h, this is actually is equal to h by mu, because whatever I have gt minus g of t minus h, so as t goes to infinity, so this goes to 1, this goes to 1, so for limiting case this has no problem, is it not? And also that contribution is 0, because both this one gt goes to 1, this is goes to 1, so as t is large enough, this is basically go to 0. And now this part I have split in a two form, a1 and a2, and now I have seen that a1 converges to h by mu as t goes to infinity. So that means this md, okay, which is the mean or the renewal function corresponding to delayed renewal process, it satisfies the Blackwell's renewal theorem for f non-lattice. This is important for f non-lattice. Okay, this is for a non-lattice case. Okay, so means one can consider many other properties and so on, but we are not going into that. So let us consider one example. So what I am considering, so consider a delayed renewal process ndt with t1 having hyper exponential distribution. Okay, that is the density function, say if I put small gt, is given by, so g of t, which is pa e to the power minus at plus 1 minus p b times e to the power minus bt for a greater than b and which is strictly positive. Okay, so hyper exponential distribution means this one, and t1 and t2 t3 and so on, they are IID having exponential distribution with parameter b. Okay, so we try to show, so then show that mdt by t, okay, this converges to b as t goes to infinity. So basically what it says that it is exactly means similar kind of thing. What is your MDT is equal to expectation ND of T. So for the renewal process case, what we have seen, which is the renewal theorem, that MT by T as T goes to infinity, that is converges to 1 by mu, no? 1 by mu, where mu is actually where mu is expectation of Ti's. So but exactly here also it is a similar kind of things. Why it is so? Because that as T goes to infinity, whenever T is big enough, that means that I can think of that it is a renewal process type of thing, because T1 only having the distributions G, and T2, T3 and all these things having the distributions F, is it not? And M, which is the corresponding the mean of the renewal process, MT, if the interregular times are T2, T3 and so on. So there actually we know that okay, it should converge to 1 by mu, and in this case mu, which is expectation of Ti's for I greater equal to 2, and then this is exponential distributed with parameter b, is it not? So that means that mu should be 1 by b, and hence 1 by mu should be just b, is it not? So that means what it says that basically if you look at the asymptotic things, even if it is the delayed means basically in the past actually we have not counted in the sense that the distributions are different. Okay, so whenever you noticed, so you don't notice the past in the sense that they have the different distributions. But as T goes to infinity for large enough, it does not matter. That is why actually it says. Okay, though it is in using your example, but one can show in a theoretical setup also. But I am saying that it is it does not differ whatever we know from there, is it not? Even if start with the distributions G and then other distribution for the interval times T, T2, T3, T and so on are same distributions, common distributions is F, but if you look at the limiting distributions, then there is no difference. Okay, so let us try to check these things. So from the renewal equation, what I know, MDT, this is my GT plus 0 to T M of T minus X D of G of X, is it not? So now these things actually I can write down GT plus 0 to T M of T minus X, then G of X dx, because the T1 it has hyperexponential distributions, that means it has a density function small g, so d of gx is gx d of x. Okay, so let us calculate this integral a. I define, which is 0 to t, this part m of t minus x of g of x. Okay, so now check, because m already you know, is it not? M is nothing but what? Because M is the renewal function associated to the renewal process associated to the interval times T2, T3 and so on. And T2, T3 they are exponentially distributed with parameter B. So you know explicitly what is my M, is it not? So you know explicitly what is my M. So you check yourself, just think of as exercise. So check that my A is nothing but minus BP by a 1 minus e to the power minus at minus 1 minus p times 1 minus e to the power minus bt plus b of t. Okay, you check yourself these things. So thus mdt, which is, if you look at, this should be bt plus p over a minus b by a 1 minus e to the power minus 80. Okay, why this is so? For that I need to calculate my g of t. So what is gt? Gt should be 0 to t g of s d of s, is it not? That is the gt, because g is the distribution function and g small g is the density function, and density function is given to you. So now you check it. This is my 0 to t p a e to the power minus as plus 1 minus p b times e to the power minus b of s whole of ds. Now if you calculate, this should be p times 1 minus e to the power minus at plus 1 minus p times 1 minus e to the power minus bt. Okay, this is my gt, and now if you plug here that mdt is equal to in this form here, then you will see from here that mdt, which is given by bt plus p of a minus b by a 1 minus e to the power minus 80. So this implies mdt by t, which is b plus p into a minus b by a 1 by t into 1 minus e to the power minus 80. Okay, so now we see that limit t goes to infinity mdt by t, because this is the exponential growth but in a negative thing, so you see that this part goes to 0, hence it is nothing but the b. So limit t goes to infinity mdt by t is equal to b. Okay, okay. So next we will talk about so-called the stationary renewal process, and then I will stop. So stationary renewal process means basically, so suppose we want to model a renewal process that began indefinitely far in the past, so that the remaining life of this item in service at the origin has the limiting distribution of the excess life, okay, of an ordinary process. So in particular, what we try to show that if the first renewal distribution or the distributions of T1, think of the delayed renewal process, so their Gx, if it is given by the distribution of the excess life, so what is that? That is basically mu inverse 1 by mu, no? 1 by mu of 0 to x 1 minus f of t dt. That is actually we have seen, no, the limiting distributions of excess life. This part actually we have, it is not, or the residual life. So what it says that, so look at the delayed renewal process where the T1 has a distribution Gx, which is given by 1 by mu 0 to x 1 minus ft dt, corresponding to the ordinary renewal process. Okay, then this renewal process is called the stationary or equilibrium renewal process. Okay, so it is a delayed renewal process with gx is given by in this form. Okay, so it is called stationary renewal process, or sometimes called the equilibrium renewal process. Okay. Okay, so again I denote this by NE. Okay, NE of T, that means the equilibrium renewal process or the stationary renewal process. And if my excess life, I denote as a NT of E. Okay, it is the excess life or the residual life of NE of T. Okay, so now my claim I put as a theorem form that the mean expectation of NET, which is my MET, this is T by mu. Okay, so what is your mu? Is expectation of T2, is it not? And second, the probability distribution over excess life, which is nu T of E, this is my G of X for all T. Okay, G of X is given by this one. That means basically the probability distributions of my whole process of the excess life of my equilibrium process or the stationary process has the same distributions as the limiting distributions of your ordinary renewal process, because G of X already we have wrote down these things is the limiting distributions of your ordinary renewal process, no, the excess life of that, excess life of the ordinary renewal process. Okay, that means this holds for all T, and hence the limiting distributions of the excess life, they are same in this case. Let us look at the proof. So like in previous case we consider the delayed renewal, so stationary renewal process is nothing but the delayed renewal process, but with particular G. So what I have that MET, this is again I have GT plus 0 to T ME of T minus X of D of Fx. Is it not? So we want to check that MET is equal to T by mu satisfies, if I just put as a star, satisfies char. So we try to show that expectation of MET is equal to T by mu. So we try to show that T by mu, it satisfies this equation. Then we are done. Is it not? Okay, so let us look at the right hand side. If I look at, so now GT plus 0 to T ME of T minus X D of Fx. This is nothing but what is my G? This is mu inverse 0 to T 1 minus f of x d of x, because this is given to you, and plus 0 to T. I try to show that ME of T is equal to T by mu satisfies this thing. So that means MET I try to write down, which should be my T minus 1 by mu of T minus X, and then I have D of Fx. Is it not? So now if you try to calculate, this is now T by mu minus 1 by mu. Now here I have, now if you do the integration by parts formula, then what we end up with, this is 0 to T T minus X D of Fx minus, first I try to write down just because 1 by mu is there, so this is 0 to T f of x d of x I have, is it not? So now I use the integration by parts formula here. Then if you look at what I have, this is t by mu minus 1 by mu into t minus x fx, which is at x is equal to 0 to x is equal to t, and then the other part, because whenever you differentiate with respect to x, so then these things got cancelled out. So I end up with only the boundary term. So this is nothing but t by mu. Okay, because at t is equal to 0 and whenever you put x is equal to 0, you have your f of 0, so that is actually is 0. So that means this is t by mu, that means mu of t. So now the left hand side is equal to the right hand side if we evaluate for mu t is equal to t by mu. Okay, so this shows that expectation of nu of t which is equal to t by mu. Okay. Okay, so to prove the second part, let us define AE of t, which is probability over nu t is greater than x. Okay, and my AT, which is same as probability over nu t is greater than x. So what is the nu t now? So nu t is the excess life or the residual life in an ordinary renal process, means corresponding to the interval times t2, t3, t4 and so on. Okay, so again if you try to write down this nu t e greater than x in a standard form, then what I have AET, okay, means you conditions with your first renewal time and so on, and then if you look at, so what I have 1 minus g of t plus x and then plus 0 to t a of t minus y d of gy. Is it not? Just look at how we have write down the renewal the residual process, no, we just conditions with the first renewal time, so that means, and then you look at the conditional things from there. So here actually you will have, because f is replaced by now g, okay, and then after that, because you have that 1 plus that probability of nu t minus x, so whenever it is happening for the first case, second onwards, so this is same as your ae of t minus y, but that is same as your a t minus y, because there is no such of g. Now all these things are like in a ordinary renal process, is it not? So because this is your t1, now you have t2, t3 and t4 and so on. So this is the first time actually the renewals is happening. So after that, whenever you are looking for here, okay, so this is your y and y is like between here to here, that means you can think of, okay, I have started from here, okay, but the interval should be now the difference of the interval, so t minus y, but that is in an ordinary fashion, is it not? Because t2, t3, t and so on, they have IIDs with distribution functions f, so you can think of from there is a renewal functions, and hence I have my a of t minus y, but with respect to d of gy. Is it not? Like exactly similar way how we have done it for the nu t case. Okay, so now this one is nothing but 1 minus g of t plus x plus g of convolution a at point t. Okay, the convolutions g convolution t at point t. This is the convolutions of a and g. Okay, so now again if I just look at at, then we will have the similar things, no, 1 minus, but g should be replaced by f of t plus x plus 0 to t, that is actually we have deduced earlier, no, a of t minus y of d of fy. What is your a? A is nothing but at, which is probability over nu t is strictly greater than x. I have put it, and then we deduce this expression there. Okay, so now this part you can write down. One minus f of t plus x plus 0 to t. Okay, 1 minus f over t plus x minus y of t of m of y. That is also we have seen it. Is it not? Hence, these things you can write down. This is my at plus m convolution with a of t, means evaluate at the point t, where my at is nothing but 1 minus f of t plus x. Okay. So thus I can write down my a of t, which I have 1 minus g over t plus x plus g of convolutions of. So now I have at. So this is, I can think of, this is my at plus m convolutions of a and t. So now this convolutions, actually if you just think of, this should be 1 minus g over t plus x plus g convolutions of at a with respect to at the point t, plus this one, it is nothing but g convolutions m convolutions a at point t. Okay, because the convolution is basically distributed. This part I have. So what I have, that gt, again what is my m of e? M of e, we have already seen that this is gt plus g over convolution of mt. So by the convolution property, this is nothing but just only the integrations. You can interchange the integrations and so on, and then look at. So g convolutions a at point t plus g convolutions m convolutions a at point t. This should be same as, because me is g plus g convolutions of mt. So this is nothing but small me convolution at. Okay, because this is g of at, g m at. That's all. Okay. So that means what I have, this implies, if you plug in again here, I have my ae of t, this is 1 minus g over t plus x, and then plus exactly this part, no, this is there. So this is nothing but my me convolutions a at point t. Okay. So this is nothing but I can write it in an integral form, which is 1 minus g over t plus x plus this is 0 to t 1 minus, because f is nothing but f of t plus x, so this is f of t plus x minus y, and then dme of y. I just write down the what is the convolution, meaning of the convolutions, and this part. So already we have seen that met is nothing but my t by mu. Is it not? Met is equal to t by mu. So what we have then, this implies my a of t, which is equal to 1 minus g over t plus x plus, now if you put it here, this is met is equal to t by mu, so 1 by mu dt you have, and now if you change this variable, I have, this is 1 by mu x to t plus x 1 minus f of y of dy. Because MET is equal to T by d mu. Now if you look at the differential of these things, then this is 1 by mu d of t. Okay, so d of y, if you put d of y, and now you change these things. Okay, so t plus x minus y is equal to some z, then you put it, so it should be from x to t to t plus x 1 minus f of y d of y. But what is my g? It is given to you, so given this is 1 by mu 0 to x 1 minus f of y over dy. Is it not? So this implies my g of t plus x minus g of x. This is 1 by mu x goes to t plus x 1 minus f of y of dy. So if I just plug here, what this implies, my a of t, this is 1 minus g over t plus x, and then plus this one I can write down, this is my g of t plus x minus g of x, and hence this is nothing but 1 minus g of x. So that means probability of AET, what is that? This is probability of nu ET is greater than x. Okay, this is equal to 1 minus g of x. So this implies probability over nu et less than equal to x. This is exactly my g of x. Okay, so that means the excess life of your stationary renewal process or the equilibrium renewal process is same as my the distributions of T1 g of x, which is the limiting distributions of the excess life of ordinary renewal process. Okay, so I'll stop today, and then in the next class, okay, so my plan was to do some applications using all these things, so we'll see. Otherwise I'll start so-called the martingale theory. Okay, any question?